Hey guys, this is lab 4 and the main objective of this lab was to use a computer model to predict the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. Um, and the main results of this lab were that using Newton's second law and the energy principle, the computer model was a good fit for the motion of the system and thus was a good predictor of the motion future of the system. Now for this lab, we had to take into account two models that affected our system. The first model is Newton's second law, and the system that we need for this is the mass that is hanging on the spring only. And to calculate the forces that are acting on the mass, we need to calculate the gravitational force of the Earth on the mass, which has the magnitude of the mass of the object times the gravitational constant on Earth, which is 9.8 meters per second squared. And this remains the same throughout the motion of the mass because these two quantities always remain the same. The second force acting on the mass is the spring force, which has a magnitude of K times S, K being the spring stiffness and S being the difference in distance between the relaxed length and the stretched length. Now this changes throughout the course of motion because S is changing, or the distance between the relaxed length and the stretched length is changing throughout the motion. The next model we need to take into account is the energy principle, which takes in as the system the mass plus the spring plus the Earth. Now, the energy principle states that the change in the total energy of the system is equal to the work done on the system by the surroundings. Now, for our experiment, this is equal to 0 because there are no interactions from the surroundings on the system. The change in E, or the change in energy of the system, is equal to the change in all of the individual energies that are acting on the system, including the change in kinetic energy plus the change in gravitational potential energy and the change in the spring potential energy. And we know that adding all of these up is equal to 0 for our system. Tracker was used to analyze the motion of the spring mass system. As we play the video, we see that the mass on the spring is moving in an arc around the spring. And so from the graph we see that both in the x and y position graphs, the motion is oscillating up and down. Now we will use a computer model to compare the experimental motion to the predicted motion. Here are some parts of the code used to create the computer model of the motion. We set the mass of the object as well as the initial position and initial velocity of the object. And we set time equals to 0 because this is when we start our observations. We set the other initial conditions such as delta t, which is very small, so we can get accurate predictions. And then we define all of our constants needed to calculate the different forces, which include the gravitational force and the spring force. And we use the equations for the forces to equate those forces and calculate them at each delta t. We use Newton's second law to find ball velocity and ball position at each delta t as well. We use the equations of the different energies to define those, and then we set delta k equals to, we set delta of each of the energies, for example delta k, delta ug, and delta us, equals to those minus the initial energies, which calculates the change in those energies at each delta t as well. In the y direction. Now let's run the computer code to see what the predicted motion of the model looks like compared to the experimental motion of the spring mass system. Here the blue ball represents the predicted motion while the red ball represents the experimental motion. We see that as the model creates this motion, the red ball is moving fairly consistently with the blue ball, which indicates that the model is a fairly good predictor of the motion of the spring mass system. Looking at the graphs of the different energies, we see that the kinetic energy, well, we see that all three energies are oscillating, and the kinetic energy is less than the potential energies of the spring represented in the red, and the potential energy of the gravitational potential energy represented in green. But when we add all of these together, we get the total change in energy, which is always zero. This satisfies the energy principle for our system, because we see that the yellow line is always on the x-axis. Here is a graph representing or comparing the experimental position to the model position. The the red experimental position is fairly consistent with the blue model position. However, there are various deviations. These could be because the model prediction is uh, is calculated every 1/210 seconds, which is very small. While for the experiment, we only calculated the position at every 0.19 seconds, and this could be a result. This is one of the reasons why there are there are slight deviations in the model and the experiment positions. We already said that our data satisfied the energy principle. Now for the second what does it mean question, we predict the oscillation period from both the x and the y position data, which we get to be 1.61 seconds for the x position data and 1.52 seconds for the y position data. The difference suggests that the oscillations occur more quickly in the y direction, meaning that the mass the mass on the spring is oscillating faster in the y direction than in the x direction.